Parametric equations. Many shapes, even ones as simple as circles, cannot be represented as an equation where y is a function of x. Consider, for example, the path of a moon follows as it orbits around a planet, which simultaneously rotates around a sun. In some cases, polar equations provide a way to represent such a path. In others, we need a more versatile approach that allows us to represent both the x and y coordinates in terms of a third variable or parameter. Parametric equations. A system of parametric equations is a pair of functions x of t and y of t in which the x and y coordinates are the output represented in terms of a third input parameter t. Example 1. Moving at a constant speed, an object moves at a steady rate along a straight path from coordinates -5, 3 to the coordinates 3, -1, and 4 seconds. Where the coordinates are measured in meters, find parametric equations for the position of the object. The x-coordinate of the object starts at -5 meters and goes to +3 meters. This means the x direction has changed by 8 meters in 4 seconds, giving us a rate of 2 meters per second. We can now write the x-coordinates as a linear function with respect to time, t. X of t equals -5 plus 2t. Similarly, the y value starts at 3 and goes to -1, giving a change in y value of 4 meters, meaning the y values have decreased by 4 meters in 4 seconds for a rate of -1 meter per second. Giving equation y of t equals 3 minus t. Together, these are the parametric equations for the position of the object. X of t equals -5 plus 2t, y of t equals 3 minus t. Using these equations, we can build a table of t, x, and y values. Because of the context, we limited ourselves to non-negative t values for this example, but in general, you can use any values. From this table, we could create 3 possible graphs: a graph of x versus t, which would show the horizontal position over time, a graph of y versus t, which would show the vertical position over time, or a graph of y versus x, showing the position of the object in the plane. Notice that the parameter t does not explicitly show up in this third graph. Sometimes when the parameter t does represent a quantity like time, we might indicate the direction of movement on the graph using an arrow as shown above. There is often no single parametric representation for a curve. In example 1, we assume the object was moving at a steady rate along a straight line. If we kept the assumption about the path, straight line, but did not assume the speed was constant, we might get a system like x of t equals -5 plus 2t squared, y of t equals 3 minus t squared. This starts at -5, 3 when t equals 0 and ends up at 3, -1 when t equals 2. If we graph the x of t and y of t functions separately, we can see that those are no longer linear, but if we graph x versus y, we will see that we still get a straight line path. Example 2. Sketch a graph of x of t equals t squared plus 1, y of t equals 2 plus t. We begin by creating a table of values. From this table, we can plot the xy points in the plane, sketch in a rough graph of the curve, and indicate the direction of motion with respect to time by using arrows. Notice that here, the parametric equations describe a shape for which y is not a function of x. This is an example of why using parametric equations can be useful, since they can represent such a graph as a set of functions. This particular graph also appears to be a parabola where x is a function of y, which we will soon verify. Example 3, sketch a graph of x of t equals 3 cosine of t, y of t equals 3 sine of t. These equations should look familiar. Back when we first learned about sine and cosine, we found that the coordinates of a point on a circle of radius r at an angle of theta will be x equals r cosine of theta, y equals r sine of theta. The equations above are in the same form with r equals 3 and t used in place of theta. This suggests that for each value of t, these parametric equations give a point on a circle of radius 3 at the angle corresponding to t. At t equals 0, the graph would be at x equals 3 cosine of 0, y equals 3 sine of 0, the point 3, 0. Indeed, these equations describe the equation of a circle drawn counterclockwise. Interestingly, these similar parametric equations also describe the circle of radius 3. x of t equals 3 sine of t, y of t equals 3 cosine of t. The difference with these equations is the graph would start at x equals 3 sine of 0, y equals 3 cosine of 0, the point 0, 3. As t increases from 0, the x value will increase, indicating these equations would draw the graph in a clockwise direction. While creating a txy table, plotting points and connecting the dots with a smooth curve usually works to give us a rough idea of what the graph of a system of parametric equations looks like. It's generally easier to use technology to create these tables and simultaneously much nicer looking graphs. Try it now. Sketch a graph of x of t equals 4 cosine of 3t and y of t equals 3 sine of 2t. This is an example of a Lissajous figure. Converting from parametric to Cartesian. In some cases, it is possible to eliminate the parameter t, allowing you to write a pair of parametric equations as a Cartesian equation. It is easiest to do this if one of the x of t or y of t functions can easily be solved for t, allowing you to then substitute the remaining expression into the second part. Example 6, write x of t equals t squared plus 1, y of t equals 2 plus t as a Cartesian equation if possible. Here, the equation for y is linear, so it's relatively easy to solve for t. Since the resulting Cartesian equation will likely not be a function, and for convenience, we drop the function notation. Y equals 2 plus t, y minus 2 equals t, x equals y minus 2 squared plus 1. Notice that this is the equation of a parabola with x as a function of y with vertex at 1, 2 opening to the right. Comparing this with the graph from example 2, we see, unsurprisingly, that it yields the same graph in the xy plane as did the original parametric equations. Parameterizing curves. While converting from parametric form to Cartesian can be useful, it is often more useful to parameterize a Cartesian equation, converting it into parametric form. If the Cartesian equation gives one variable as a function of the other, then parameterization is trivial. The independent variable in the function can simply be defined as t. Parameterize the equation x equals y cubed minus 2y. In this equation, y is expressed as a function of y. By defining y equals t, we can then substitute that into the Cartesian equation, yielding x equals t cubed minus 2t. Together, this produces the parametric form. X of t equals t cubed minus 2t, y of t equals t. In addition to parameterizing Cartesian equations, we can also parameterize behaviors and movements. Example 11. A light is placed on the edge of a bicycle tire as shown, and the bicycle starts rolling down the street. Find a parametric equation for the position of the light after the wheel has rotated through an angle of theta. Relative to the center of the wheel, the position of the light can be found as the coordinates of a point on a circle, but since the x-coordinate begins at 0 and moves in the negative direction, while the y-coordinate starts at the lowest value, the coordinates of the point will be given by x equals negative r sine of theta, y equals negative r cosine of theta. The center of the wheel, meanwhile, is moving horizontally. It remains at a constant height of r, but the horizontal position will move a distance equivalent to the arc length of the circle drawn out by the angle s equals r theta. The position of the center of the circle is then x equals r theta, y equals r. Combining the position of the center of the wheel with the position of the light on the wheel relative to the center, we get the following parametric equation with theta as the parameter. X equals r theta minus r sine of theta equals r of theta minus sine of theta. Y equals r minus r cosine of theta equals r multiplied by 1 minus cosine of theta. The result graph is called a cycloid.